Hello, Eastview Scholars, and welcome to this edition of Sharp Shorts, where we're going to take a quick look at chemical bonding. Now, you've probably heard a lot about ionic bonds, covalent bonds, different types of bonds through other science courses you've had. Really, we need to narrow it down to one thing. Ionic bonds, covalent bonds, metallic bonds, while there's slight differences in how the atoms interact, really that's about properties. The reality is here is you have these atoms like you have here in this picture. Now, by the picture, this is technically probably a covalent bond just because their electron orbitals are overlapping in their electron clouds. But really, here's what we know. An atom has a positive nucleus and it has electrons outside an electron cloud. These electrons are held into this atom by the attraction of the negative electron to the positive thing. But when you have bonding, these electrons are also attracted to the nucleus of a different element. Okay? So a chemical bond is really a chemical bond. It's the attraction of electrons not only to their own nucleus but another. Now, what properties that yields makes them different. The bonds, though, as noted here in the notes, are defined by their difference in electronegativity of the elements. So let's look at this. Here is, when we talked trends of the periodic table, we talked about how fluorine here is the most electronegative element, and it was given a number 4. And then all the other numbers for all these elements were derived off of the fact that fluorine was the most electronegative. What they do then in defining a bond is those that are most ionic, or defined by ionic, the elements you're comparing have a difference of 1.7 or greater. Okay? Covalent bonds are bonds where that electronegativity difference is below 1.7, down to 0 for your diatomic elements. You can see here that if bromine were to bind with itself, 2.8 minus 2.8 is 0. That's a truly polar, non-polar covalent bond. Anyhow, that just gives you, that's by definition what it is. And the reason I say that a chemical bond is a chemical bond is a chemical bond, who cares what goes on here, is that if you're around that 1.7 border, like water is technically covalently bonded, but it acts very ionic and has huge interactions as a solution solvent for ionic compounds. And you know, there's ionic compounds that can have some covalent type properties. So there is some connection to all of it. Remember that ionic bonds are metals and nonmetals, so everything here in blue to anything here in yellow, including the hydrogen, which is over here in its 1s1 electron column. And covalent bonds are things that are two nonmetals. So all the orange stuff here, covalently bonds. So you can see just by the numbers how that's going to work. That is what it is by definition. But I think the thing to understand is just it's the properties that those compounds have that more defines whether they're ionic or covalent. Anyhow, so here it is. An ionic bond has an attraction difference greater than 1.7, and how they identify that then is that what they're saying is that one element completely gives up its electron to empty, for example, here's sodium, starting with 11 protons and 11 electrons. It certainly would want to get rid of this electron and have that, see the rest of its shells below then are full, and it has the noble gas configuration of neon. Chlorine, on the other hand, would much prefer, since it has 7 valence electrons, to pick up an electron and then end up here with filling its shell and having a noble gas configuration much more stable. And in doing so, since sodium has dropped an electron, it now has a +1 charge. And in doing so over here, chlorine now has a -1 charge. And so you have this positive and negative element, and you have this electrostatic interaction here. That is an ionic bond. Okay. So when they talk about ionic bonds, another way that they define them is that one element completely gives up its electron, another element, an anion, picks it up. Cations get rid of it, anions pick it up. Okay. And it leads to properties that they have for it, which we'll see later, things like conducting electricity and stuff. Covalent bonds, on the other hand, are when things share. And you can see here by the drawing difference, you've got electrostatic attraction here. Covalent bonds, they overlap their electron clouds and they share electrons. And they're doing the same thing that any compound or element wants to do. They want to share enough electrons to fill out their octet and get a more stable form. And so they will share as many as they have. Covalent bonds far surpass ionic bonds in the compounds, the millions of compounds that are out there, in how they do. Anyhow, as it says, a bond resulting from the sharing of electron pairs between atoms, no ions are formed in this bond because they wouldn't be. And remember, as we go back and take a look at it quick, you're looking at nonmetals. These things form anions, negative ions. They're not going to form an ion and bond to another negative. Things with the same ionic charge will not bind together. It's opposites that attract. Just ask my wife. There are then defined, there are two types of bonds, polar covalent and nonpolar covalent. Most covalent bonds are polar, and it just comes from the fact that when you have, even though these things are sharing their electrons, their nuclei, now this picture looks like a diatomic element. It looks like you've got a couple of halogens here where the nuclei are the same thing. Polar covalent bonds happen, for example, in water. Oxygen is a much bigger atom with a much stronger nucleus than hydrogen. And so one oxygen shares electrons with two hydrogens. That's where H2O comes from. What's going to happen is, and we'll see this more when we look specifically at covalent naming, but what you see is that the electrons, while they're never taken out of a single atom's electron shell, they do get pulled closer to the stronger atom. And that leads to a polarity, okay, which you can see here with hydrogen and chlorine. Okay. Chlorine is much bigger and stronger, so they are sharing these two electrons. Okay. But this has a much stronger nuclear charge, more effective nuclear charge. So it's not going to rip the electron away from the hydrogen. All it's going to do is it's going to pull closer into the chlorine electron cloud and a little farther away from the hydrogen. And what you get here is what's called a dipole moment. So the hydrogen side will be a little positive because its electron has been kind of pulled away from it. So you have a little bit of that nucleus looking like a positive charge. And with that electron getting pulled very close into chlorine's electron shell, then it's going to give chlorine a little negative, what's called a dipole moment. And so that's going to give the molecule a bit of a polarity. Same thing happens with water as oxygen pulls on the hydrogens. Here you can see two chlorines that are diatomic. Since their nuclei are the same exact strength, they're going to evenly share those. But going back to your notes, that's the difference. Nonpolar pure covalent bonds are really things that have almost the same electronegativity, or they do have the same in diatomic elements. Carbon and hydrogen are also, for all those organic compounds, carbon and hydrogen have almost a completely similar electronegativity, so those bonds are nonpolar. Okay, and that gives them different. But the key is they're sharing. They may not share those electrons equally. They may pull on them differently. And again, we've been here, but we'll look at the examples here of what we have. We have a nonpolar covalent bond where they're being shared equally. We have a polar covalent bond where the chlorine just has a little more pull on the electron, creating that dipole moment. And here we have the ionic bond where we had a transfer of electrons, and then the electrostatic interaction creates the bonding. And here's the properties that I told you about. Ionic compounds are, and we're going to focus non-metal and metal. That's really what it is. There are metal-metal. When you have two metals near each other, there is an ionic type bond, but it's more called a metallic bond. We're not going to examine that, and it's just the interaction that holds metals together. It makes metals what they are. Covalent, non-metals, two non-metals. Here, total transfer of electrons, so you get a positive, negative, and have that electrostatic interaction. And here, shared electrons. These then ionic properties are high melting and boiling points, which brings the metal-metal interaction into that, because it is, metals do have high melting points, so the atoms themselves in that metal solid are having a ionic type interaction. Covalent bonds, low melting and boiling point and stuff like that. Solids, liquids. So you can see that their properties follow kind of what they are. Many of these properties are properties of nonmetals themselves. Many of these properties are properties of the metal, and even though it's bonded to the nonmetal, it is holding on. Ionic bonds are very strong. Covalent bonds are weak. Ionic are soluble in water. Covalent are generally insoluble. But again, these are properties that as you get close to that border are not necessarily perfect. Again, water is covalent, but it does conduct electricity and stuff because it's right on the border. Anyhow, that gives you a good idea of ionic and covalent, what a bond is and what their properties are. So scholar up, Eastview.